Welcome to the Explainer. Today, we're cracking open the electrician's toolkit to really get a handle on the logic of how energy flows. We're going to move way beyond just simple formulas and build a solid problem-solving strategy for pretty much any electric circuit. And we'll use some awesome intuitive analogies to help guide us. So here's our game plan. First, we'll lock down the two unbreakable laws that are the foundation for everything. Then, we'll build a four-step algorithm you can use to solve any circuit. After that, we're going to explore three really clever tools: a kind of balancing act for resistance, an almost perfect measuring device, and then, believe it or not, we'll see how to build our own meters right from scratch. Okay, let's dive right in. What happens when circuits get super tangled and good old Ohm's law just isn't cutting it anymore? Well, you have to go back to the absolute basics. And the basics are these two foundational principles that honestly, they never ever fail. Kirchhoff's laws.
Okay, so the first rule is all about something called the conservation of charge. And this analogy right here is just perfect. Think of any point where wires connect in a circuit, any junction, as a busy train station. The total amount of current flowing in has to equal the total current flowing out. It's that simple. Charge can't just appear out of nowhere or vanish into thin air. It's basically an accounting rule for electrons, and it's non-negotiable.
Now, the second rule is all about the conservation of energy. So imagine you're swimming in a big loop in a river. When you go with the current through a resistor, your energy, we call it potential, it drops. If you try to swim against the current, you have to work harder, right? So your potential rises. And if a battery gives you a nice push, well, your potential goes way up. So this law says that by the time you swim one full loop and get right back to where you started, all those energy drops and all those energy rises have to perfectly cancel each other out. Your net change in energy is zero, period.
Now, what's really cool is how we can take these two super powerful laws and turn them into a foolproof, step-by-step algorithm, a process you can use to solve even the most intimidating-looking circuits. Let's see how that works. This four-step process, this is your secret weapon. First, label everything. Give every junction a name so you don't get lost. Second, figure out your currents, but do it logically so you use the fewest variables possible. Third, pick any closed loop you want. And finally, and this is the most important part, apply those sign rules we just talked about, strictly. Don't guess, just follow the rules. This whole process turns what looks like a messy puzzle into a straightforward set of equations you can actually solve. So now you've got the rules and a strategy, but what about the actual tools of the trade? Let's take a look at our first specialized device. It's a really clever piece of engineering designed for one thing: to precisely measure an unknown resistance. And this slide just shows the concept beautifully. On the left, you see the theory, the Wheatstone bridge. You can think of it like a balancing scale, but for resistance. You just adjust the known resistors until that little meter in the middle, the galvanometer, reads zero. We call that the null point, a perfect balance where no current flows through that center path. And when you hit that balance, you can calculate the unknown resistance with a simple ratio. Then, on the right, you see how it's actually built in the real world, as a meter bridge, which uses a long wire to find that same perfect balance point. But here's a really tricky problem you run into in physics. What if the tool you're using to measure something actually changes the thing you're trying to measure? A standard voltmeter actually has this problem. But there's a solution, and it's one of the most elegant tools you'll find in a lab: the potentiometer. The key difference is laid out right here. A standard voltmeter, well, it has to pull a tiny bit of current from the circuit just to get a reading. But the very act of drawing that current can slightly change the voltage you're trying to measure. It kind of corrupts the data. The potentiometer, on the other hand, it works by finding a null point, just like that Wheatstone bridge. And at that exact point, it draws zero current. Absolutely none. This means you get a perfectly ideal measurement of the potential difference, and that is so critical in science when you need precision. And it all works because of one simple, beautiful principle. If you have a uniform wire, the voltage drop is directly proportional to its length. The further you move along the wire, the more the potential drops. It's a straight line relationship. And this simple fact lets it do incredibly precise things, like comparing the exact voltage of two different batteries, or even measuring the tiny, hidden internal resistance that's inside a battery cell itself. In fact, you probably use this principle every single day and don't even realize it. You know the volume knob on a stereo? Or a dimmer switch for a light? Yep, those are just simple potentiometers. When you turn the knob, you're just moving a contact along a resistive strip, tapping into a different voltage based on the length. You're literally dividing the voltage.
Okay, for our final section, let's get our hands dirty, metaphorically speaking. We're going to pop the hood on the two most common meters out there, the ammeter and the voltmeter, and see how they're both built from one single super sensitive core component. And this is it, the galvanometer. Think of it as a hypersensitive current detector. It is fantastic at spotting even the tiniest amounts of current and can even tell you which direction it's flowing. But it has a big problem. It's delicate. It has a high internal resistance, and it just can't handle large currents. It would just burn out. So it's a great sensor, but it's not a workhorse.
So how do we make it useful? Well, to turn it into an ammeter that can measure big currents, we give the current an easy detour. As you see on the left, we add a path with very low resistance, called a shunt, in parallel. Now most of the current zips right through the shunt, bypassing the delicate galvanometer. To make a voltmeter, on the right, we do the complete opposite. We need to protect it from high voltage, so we add a resistor with a very high resistance in series with it. This chokes off the current and keeps the galvanometer safe.
So, the big takeaway here is that all of this stuff is connected. From those fundamental rules we started with, Kirchhoff's laws, all the way to the clever design of an ammeter, it's all just brilliant applications of the same basic logic of how charge and energy move through a circuit.
And that leaves us with one final thought. Now that you have this toolkit for understanding the flow of energy, start looking around. What other technology that you use every single day, from your phone charger to the entire electrical system in your car, is just another clever application of these simple, powerful, and universal rules?